Hello everybody. Today we're going to talk about circular motion, and we're going to take a look at a sample problem of a car on level road. So as we progress through circular motion, we're going to start to look at different examples, and one of the first examples that we usually take a look at is a car on level road. So when you see level road, what could the alternative be? Well, the alternative could be something like a banked curve, where the normal force that the road exerts up on the car is not in line, on the same y-axis as the weight force. But on level road, you would have your mg, your weight force, right in line with your normal force. So I think that's a pretty good place to start. So the example we want to look at, a car is about to go around a sharp curve with a 22-meter radius of curvature on level road. It's raining and the coefficient of friction between the road and the tires is 0.6. Find the maximum speed that the car can have to make the turn without skidding. So even though this may be a new topic of circular motion, we want to solve this problem using the expert problem-solving strategy. So the first thing we want to do is make a sketch. And I know that you're a big fan of my artistic sketches here. You're probably not. But we know from the problem that the coefficient of friction is 0.6. And we also know that the radius is 22 meters. And we're looking for the maximum speed. We're looking for V. When we were presenting similar problems in class, I had students ask me, Mrs. Carroll, I don't know about this problem. I mean, you're not given the mass of the car. And if you're not given the mass of the car, it's usually because it's not necessary to solve the problem. So let's see if that's the case for how we analyze this problem. So once I have my sketch and I have the knowns from the problem, I want to think about if there's any other physical quantities that I know. Because this object is going around this sharp curve here, then the acceleration at this point is towards the center of the circle. So I may not know quantitatively what acceleration is, but I know that the vector points this way. If I want to analyze all of the forces exerted on the car, I can set up my force diagram and I ask myself, okay, well, what's touching the car? The road is touching the car, definitely. And so the road exerts a normal force on the car. And when you have this car going around in a curve, there is no acceleration in the y direction. So the acceleration in the y direction is 0. So therefore I know that the F net in the y direction is 0 newtons. The acceleration in the x direction we've noted over here is to the right. So because of that, we know that whatever we do get for F net, let me just separate these for you. For F net in the x, it's going to be to the right. All right. Because acceleration in the y is 0, I know that mg is going to be the same length as the normal vector. So here's our mg, or the weight of the car. I also know that the surface, this road surface, exerts a frictional force on the car. So as this car travels around the curve, these tires turn. And what's interesting about as this happens, as these tires in the road are interacting, the force of friction at this point will be this way, in line with the acceleration vector that we have here towards the center of this circle. So here is our force of friction. And if this is mg here, then normal force, right, is equal to mg in the opposite direction. friction force is normal times mu times the coefficient of friction. And we were actually given coefficient of friction in the problem. So for F normal, I know that that's equal to mg, and I know that this here is going to be mu. And again, this was given in the problem. So the force of friction is equal to mg times 0.6. When I look at my force diagram, I can see that mg and normal force are balanced. And force of friction is our net force in the x direction. So net force in the x direction is equal to the frictional force. And this force, this net force, is also towards the center of the circle. This is the net force that's causing this object to continue moving in a circle with uniform circular motion. So here, in this case, our frictional force is our centripetal force. Ultimately, I'm looking for the speed. And I know that if I have centripetal force, I have mv squared over r. And in this case, our centripetal force is equal to our frictional force. So in other words, mv squared over r is equal to our frictional force, which we have as mg times 0.6. M is not given in the problem, and v squared is what we're looking for. So our mv squared stays how it is. The radius is given in the problem as 22 meters. When I see this meters and I see this mass above it, it's very easy to get them confused. Mass here is a physical quantity, where this m here is just a unit. So until we're kind of comfortable with this, I'm going to put the units here in red just to kind of make sure that we're all on the same page here. And it really is something to think about. Here I have mg, right? And I know that g is 10 meters per second squared. So I can have m times 10 meters per second squared times 0.6. So I end up with mv squared over 22 m is equal to m, this m being mass. 10 times 0.6 will just give us 6. So m times 6. Now, coefficient of friction is no units on it. Our acceleration due to gravity has meters per second squared. And again, those are units. And until everybody's comfortable with these procedures, I just want to highlight my units in red. Okay, I wouldn't want this m here for meters to be confused with a physical quantity of mass. So I'm just going to keep that the way it is. My ultimate goal here is to get b squared by itself. So at this point, I'm going to cross multiply what I have. So I have mv squared is equal to 22 meters times 6 meters per second. So you have your 22 times 6 is going to give you 132. So this will be 132 meters squared per second squared times mass. And again, I just want to highlight those units. All right. I'm going to divide m out. So I have this m cancels. So I end up over here. I'm just going to follow this up over here. I end up with v squared equal to 132 meters squared per second squared. And those units make sense to me because if I'm taking the square root of v squared so that I can obtain a value for v, I want to take the square root of 132, which is 11.49. I think there's two significant digits given in the problem here, so I'll leave this as an 11 here. It's about 11. And then the square root of meters squared per second squared gives you meter per second. So the maximum speed that the car can have and still make this turn without skidding is 11 meters per second.